Nestled in the picturesque city of Geneva, Switzerland, the European Organization for Nuclear Research, commonly known as CERN, stands as a beacon of scientific exploration and discovery. At the heart of CERN's mission lies the quest to understand the fundamental constituents of matter, from the tiniest particles to the vast cosmic expanse. One of the most extraordinary scientific projects here is centered on the captivating tale of the Anoma factory, where visionary thinkers are stretching the boundaries of human understanding and technological prowess. Antimatter, as we know, is at the heart of a mystery about why the universe exists at all. So studying antimatter is also key to understanding our very existence. But in a quest to unravel one of the biggest cosmic mysteries, CERN has found something weird happened with antimatter that no one can explain. This finding then leaves a hanging puzzle that scratches scientists' heads. So what did exactly they find alarming? Join us as we dig deeper into CERN's new discovery that has the scientific community baffled. Antimatter sounds like science fiction, a material that looks like ordinary matter but would unleash as much energy as an atomic bomb if even a speck of it came into contact with anything around us. Small wonder that the scientist who first predicted the existence of antimatter felt uneasy about what he had found. Nowadays, physicists are using gigantic particle detectors to probe subtle effects that they hope will explain the central mystery of antimatter. Where has it all gone? It is a question whose solution lies in the very first moments of the Big Bang almost 14 billion years ago. Something happened back then to turn a universe born with as much antimatter as ordinary matter into one strangely devoid of the stuff. Did the antimatter vanish as the result of some strange quirk in the laws of nature? Or is it still out there somewhere making up antimatter in an orbit around anti-S? One thing is certain. Despite its weirdness and rarity, antimatter is for real. The first hints of antimatter's existence emerged in 1928 when 26-year-old British physicist Paul Dirac announced his discovery of a single equation unifying no fewer than three of the key theories of physics: quantum theory, electromagnetism, and Einstein's special theory of relativity. In 1928, Paul Dirac made his astounding claim, making antimatter the focus of unprecedented attention. It was a spectacular achievement and one that won Dirac a Nobel Prize. But its implications were perplexing. Like quadratic equations familiar from school maths, Dirac's equation had not one but two solutions. One of them made perfect sense and described the properties of that most familiar of particles, the electron. But the other solution seemed to describe another subatomic particle whose properties were the exact mirror image of the electron, with the same mass but opposite electrical charge: an anti-electron. What worried Dirac was that no one had ever seen such a particle or anything like it. Even so, he decided to put his trust in his equation and regard the new particle as a prediction. Dirac's faith was quickly rewarded. In 1932, physicist Carl Anderson at the California Institute of Technology had developed a new type of particle detector to study cosmic rays, incredibly fast particles hurtling through the atmosphere from deep space. A photograph taken with a detector revealed something utterly bizarre: the trace of a particle behaving as if it were the exact mirror image of an electron. It was the first sighting of the particle predicted by Dirac's equation 4 years earlier, identical in mass to the electron but with a positive charge. It was duly dubbed the positron. But the discovery only served to highlight the mystery of antimatter. While electrons are ubiquitous, it took a state-of-the-art particle detector to find even a single positron. There was nothing in Dirac's equation or in the known laws of physics to explain why the universe should prefer matter to antimatter. So where was it all? One suggestion was that the Earth just happened to lie in a relatively antimatter-free region of the universe. Perhaps there were whole stars made out of the stuff lurking out there. If so, it would be easy enough to tell, for as soon as antimatter comes into contact with ordinary matter, it is totally destroyed in a huge burst of radiation. Einstein's famous equation, E equals mc squared, shows that if just a single gram of antimatter comes into contact with ordinary matter, the energy released is equivalent to the detonation of an atomic bomb. In fact, matter-antimatter annihilation is the most potent source of energy in the universe, and its effects are hard to miss. So if there really are anti-stars or even whole anti-galaxies beyond our own, the Earth should be bathed in a constant glow of gamma radiation, the telltale sign of matter-antimatter annihilation. The reality could hardly be more different. Since the early 1960s, Astrophysicists have sent ever more sophisticated gamma-ray detectors above the protective blanket of the atmosphere to see what is out there. And the message has been consistent. There are no signs of antimatter objects anywhere in the universe. The lack of gamma rays from our own galaxy suggests that the nearest anti-star must be at least 10 light-years away, with no more than one star in 10,000 being made from antimatter. On a larger scale, the absence of antimatter is even more striking. The level of gamma rays coming from distant galaxies suggests that no more than 1 part in 100,000 of extragalactic matter can be in the form of antimatter. But why is there more matter than antimatter? Did something happen during the Big Bang to get rid of antimatter while leaving enough ordinary matter behind to create the galaxies, stars, and us? The first hint of what that something might be emerged in 1964 when American physicists studying so-called kaon particles discovered a bizarre effect called charge parity, or CP violation. This meant that antimatter does not always perfectly mirror the properties of ordinary matter. The level of CP violation detected was very small, but in 1967, the brilliant Soviet physicist and dissident Andrei Sakharov showed that it might just explain why matter created in the Big Bang did not pair off exactly with all the antimatter. But 2 big question marks hung over Sakharov's suggestion. Firstly, to stand any chance of explaining the mystery of antimatter, CP violation had to apply to more than just kaons. And secondly, even if it applied to all particles, the effect had to be strong enough to explain the huge preponderance of matter over antimatter that we see today. Physicists are now probing both these questions in gigantic machines that attempt to recreate conditions in the early universe. At Stanford University, California, the 1,200-ton Bobber particle detector is being used to study the effects of smashing together electrons and positrons with a violence not seen since moments after the Big Bang. The collisions produce unstable particles called B-mesons and their antimatter counterparts, whose decay can be studied for signs of CP violation. In 2001, scientists working at Bobber and also at Bell, a similar experiment based in Japan, announced that they had succeeded in detecting CP violation among B-mesons and their antiparticles, thus showing that the effect is not confined to one type of particle. Better still, the level of CP violation was right in line with theoretical calculations based on the so-called standard model, the best theory currently available for understanding subatomic particles. The bad news was that the measured level was far below that needed to explain the observed preponderance of matter over antimatter in our universe. Physicists are taking this as a sign that the standard model is lacking something crucial. Precisely what it might be remains unclear, but experiments are already being planned to find out. Astrophysics and particle physics are often dismissed as being utterly irrelevant to everyday life, but by attempting to explain how antimatter lost out to ordinary matter at the birth of the cosmos, they hold the key to understanding our very existence. That's also why physicists at CERN are searching for subtle ways that antimatter differs from matter. Indirect measurements of the effect of gravity on antimatter suggest that matter and antimatter both respond in the same way to gravity. However, the difficulties of working with antimatter meant that a direct observation of antimatter falling freely under Earth's gravity had not been made. While antimatter can be made in the lab, it will annihilate upon contact with matter in an experimental apparatus. So great care must be taken to accumulate enough antimatter to do an experiment. And for the last 20 years, scientists from the Alpha Group have been collecting antimatter at CERN, siphoning high-energy antiprotons from collisions in the CERN proton synchrotron and slowing them from the speed of light to speeds of a few hundred feet per second and a temperature about 15 above absolute zero. The antiprotons are then mixed with a cloud of anti-electrons or positrons produced by the decay of radioactive sodium in a so-called mixing trap. Controlled by electrical fields, normal hydrogen, the simplest and most abundant element in the universe, consists of a positively charged proton attended by a negatively charged electron. The alpha experiment results in a few atoms of antihydrogen. The nucleus is an antiproton and a positron circles it. In 22, Dr. H reported that these antihydrogen atoms emitted and absorbed light at the same frequencies and wavelengths as regular hydrogen, just as Einstein would have predicted. Since then, many experiments, all indirect, have strongly suggested that antimatter also gravitates normally. But those experiments have not been conclusive because gravity is less than 1/1,000,000th as strong as the electromagnetic fields used to manipulate the antiatoms. In the latest experiment, the antihydrogen atoms were confined by a magnetic field inside a 10-inch long metal container. Since, like hydrogen, antihydrogen atoms carry a slight magnetic field of their own, they bounce off the walls of this bottle. The magnetic fields can also be tuned to countergravity and suspend the antihydrogen atoms in the bottle. In the experiment, when the fields were slowly ramped down, the atoms eventually escaped the field and annihilated themselves in a flash on the walls of the chamber. About 80% of these flashes occurred below the chamber. According to statistical analysis, this suggests that gravity typically acts to pull antiatoms downward, just as it would with normal matter. Any violation of the expected symmetry between hydrogen and antihydrogen would have rocked physics to its core. However, that did not happen. In the words of Dr. Jonathan W., a physicist at the University of California, this experiment is the first time that a direct measurement of the force of gravity on neutral antimatter has been made. It's another step in developing the field of neutral antimatter science. But the result leaves another puzzle hanging. According to relativity and to quantum mechanics, the two quarreling theories that rule the universe, the Big Bang should have created equal amounts of matter and antimatter, which should have annihilated each other long ago. But our universe is all matter, with not a speck of antimatter to be found outside of cosmic ray showers and particle collider collisions. So what happened? Why does the cosmos contain something rather than nothing? The question has burned for almost a century already. 4 years ago, an experiment in Japan involving the strange particles known as neutrinos reported what might be a clue to the cosmic imbalance. At the Large Hadron Collider, an entire instrument called LHCb is devoted to searching for any differences between matter and antimatter that could have tipped the cosmic balance. Asked whether the results from the ALPHA experiment offered any insights for the LHCb team, as Drive W. said, "Since our answer is consistent with normal gravity, I don't think it gives any hint. Unfortunately," which is another way of saying, we still don't know why we're here. While antimatter still is a puzzle, some interesting ideas come to our mind. We all know that the birth of the universe in the Big Bang, 13.8 billion years ago, marked by a period of extremely rapid expansion and creation of both matter and antimatter particles in equal amounts. Matter and antimatter particles undergo mutual annihilation, releasing vast amounts of gamma radiation. Absolutely perfect annihilation is blocked by a combination of the expansion of the universe and the effect of CP violation, ensuring more matter survives than antimatter. Radiation leaves a fingerprint in the number of photons to particles in the cosmos, as seen in this cosmic microwave background, suggesting matter and antimatter annihilated each other to within 1 part per billion around 9 billion years after the annihilation process ends. Around 10 to the 57th particles of matter come together under gravity to form the solar system. So what if the universe were made up entirely of antimatter? To answer this, we must first recognize that every subatomic particle has an antiparticle with opposite properties. The antiparticle of the negatively charged electron, for example, is the positively charged positron. Antiparticles can combine to make antiatoms and ultimately antimatter. Crucially, though, the photon, the particle of light, is its own antiparticle. Consequently, if the universe were made of antimatter, it would look no different. So how do we know the stars are not anti-stars and the galaxies are not anti-galaxies? Well, when particles of matter and antimatter meet, they annihilate each other. Their mass energy flashes into high-energy light or gamma rays. We know there are no anti-stars in our galaxy or anti-galaxies in the local group because matter mingles within these systems, yet we see no annihilation radiation. It looks as if we live in a universe of matter. This is a mystery because particles and their antiparticles are always created together. So why does the universe not contain a 50-50 mix of matter and antimatter? A clue comes from the fact that there are about 30 billion photons for every particle of matter. This can be explained if in the Big Bang 30 billion and 1 particles of matter were created for every 30 billion particles of antimatter. After annihilation, there would be no antiparticles and 1 particle from every 30 billion photons. So is there a fundamental asymmetry in the laws of physics that slightly favors the production of matter over antimatter? Remarkably, yes, and its name is CP violation. Currently, experiments are underway to see whether the asymmetry is big enough to account for our matter-dominant universe. In action, the universe made of antimatter, as told, would look no different from our current universe. So what if there were an antimatter black hole? Would there be anything different about it? Well, in fact, according to Einstein's general relativity, black holes don't particularly care what they are made out of. If you put a sufficient amount of mass together in a small enough volume of space, the gravitational pull within that region will prevent anything below a certain speed from escaping. Dial up the amount of mass, and it becomes harder and harder to escape. You'll have to move even faster to do so. And for better or worse, there's a limit to how quickly anything can move within our universe. The speed of light in a vacuum. Whenever the speed needed to escape a region's gravitational pull is greater than the speed of light, that's the necessary condition for creating a black hole. In fact, the event horizon is defined by the border from where you can't escape. In one of the more famous theorems in general relativity, there are only a few types of properties that a black hole can remember. They include mass, electric charge, angular momentum, and if it was to exist, magnetic charge. And these properties are known as the types of hair a black hole can have.